solubility is affected by intermolecular forces. Remember that we said that the intermolecular forces are important because they affect a lot of physical and chemical properties. And one of them is solubility.
Now here's something we hope you'll really like.
Now, you probably heard this little saying before, like dissolves like. Well, that comes from the idea of solubility, because what we see is that ionic or polar solutes will be soluble in polar solvents. But that's not the case when you mix the two. It's not, ionic or polar solutes are not likely to dissolve in non-polar solvents. It's just the opposite. Non-polar solutes will be soluble in non-polar solvents. Okay, so for example, that is why, sugar, which is a polar molecule, dissolves readily in water, which is a polar solvent. And that explains why when you put oil and water, they don't mix together. They form separate layers. So I think I already told you this in lesson 1, but just to get it in the notes and to make sure that everybody understands this, that when you start looking at larger molecules, it's not as easy to analyze them for perfect symmetry or asymmetry. So there is an easy way to identify a polar molecule, a molecule with a permanent dipole, if it's like a large organic molecule.
Argumental?
So any sort of organic molecule, which by that you'll notice that because it has carbons in it. If it has an oxygen or a nitrogen, it will most likely be polar. So you have some examples already there in your handout. But all of these, if you'll notice, they have a nitrogen or an oxygen, okay? And because these have lone pairs on them, they orient themselves in a way where they end up with a permanent dipole. And so the opposite of that is a nonpolar molecule is going to be one without oxygen or nitrogen. And so it would be something that just has carbon and hydrogen in it. So multi-carbon molecules that have carbon and hydrogen are nonpolar. And so once again, you have an example there already printed in your handout. But this would be a non-polar solvent or solute, however it was being used. Okay, now sometimes it's not as simple as just saying, oh, well, polar solutes dissolve in polar solvents, because sometimes you have to take into account all of the intermolecular forces that are in play. So all the intermolecular forces must be considered when you're predicting the solubility of a large molecule. And that can be seen with different types of alcohol. And if you take organic chemistry, you'll learn what I mean by that. But an alcohol is a classification of organic compounds. And so an alcohol is characterized by this OH group. So any sort of organic molecule you have where you have an OH group in it is an alcohol. And so if you are mixing together ethanol, which is a 2-carbon alcohol, in water, it's completely miscible. And remember what that means. It means that they dissolve each other, they mix together perfectly at any ratio. But then if I make that carbon chain a little longer with pentanol, so it's now 5 carbons, then there's a limit to the solubility, okay? It's now only 2.7 grams of it that will dissolve in 100 mils of water. And then it gets worse if you take that out to a chain of 8 carbons. So octanol, it's only 0.06 grams of it will dissolve in 100 mils of water. So we would call that sparingly soluble. Okay, so if you think about it, all of these has something in common with water. They have that OH, right? So in that sense, it is like water, like dissolves like, but it gets less and less soluble because of this other part of the solute. Okay, it's becoming, as a compound, less and less like water. So there are different things at play here. So first of all, the reason why it's becoming more and more difficult to dissolve those alcohols as you increase the length of that carbon chain is because of the extensive amount of London dispersion forces that's occurring here between the two carbon chains into in this case, octanol molecules. Okay, so there's these London dispersion forces that occur between those two carbon chains, and that's pretty strong. So they want, because there's so many of those atoms involved, and because they overlap well, remember the whole analogy of the lasagna noodles versus the billiard balls, right? So this is a perfect case of a lasagna noodle type situation. So there's extensive London dispersion forces going on there. So that's going to require quite a bit of energy to separate those two molecules. And remember, that's what dissolving something essentially is. If you dissolve table salt, or you dissolve sugar, or you dissolve octanol, essentially what you have to do is you have to separate those molecules away from each other. And so that's going to be hard to do because of the extensive London dispersion forces involved in this particular molecule. All right. So that leads to a couple new terms that we need to talk about that involve solubility. So this part of the molecule we're going to call hydrophobic, which comes from the Greek water fury. And so those extensive London dispersion forces basically repel water. But that doesn't change the fact that we still have part of this molecule that is similar to water, and we call that hydrophilic, or water loving. And so that's the part that attracts water. Okay, so we have a part of the molecule that repels water. We have a part of the molecule that attracts water. And so that leads to some interesting configurations. So for example, soap. So soap is a perfect example of this hydrophobic and hydrophilic at play. So with a soap molecule, usually the soap is an ion. It's an ionic compound, but just part of the ion, and usually the negatively part of the ion, it has a long carbon tail, and so that's called the hydrophobic tail. But then what we call the hydrophilic head of the soap molecule is either very polar, or it's many times an ion, a negative ion. And so that's going to be attracted to the polar solvent water. And so all of the hydrophobic tails kind of turn in on each other, and they form what's called a micelle. This structure is called a micelle. So it's a soap bubble, right? And so if you think about dirt or grease or oil that you have on your body, this is how soap works. So because these are usually non-polar type molecules, they get trapped into the hydrophobic part of the micelle. And so that allows the water, which is surrounding this micelle, to just take it away. Okay, so once the dirt gets trapped into that hydrophobic part of the micelle, the water can just wash the whole soap micelle away, and that's how soap cleans. Okay, so soap molecules is one application of this hydrophobic, hydrophilic concept, but we see it in other important places. So for example, every cell membrane is a bilayer of molecules that have hydrophobic tails, phospholipids, and hydrophilic heads. Okay, and so the hydrophilic heads point towards the outer part of the cell, away from the cell, and then towards the inner part, which is also a water and aqueous solution, cytoplasm, right? So this, is that barrier to the cell, and then there's specialized proteins that exist in the cell membrane to help transport necessary, nutrients and other molecules in and out of the cell. Okay, so the cell membrane. This is not part of your handout because I just want you to, to use it as an example to help you understand the idea. It's not something that I'll be quizzing you on specifically. But, if you're a biology major, then you probably have heard this stuff before, and you certainly could be quizzed over it in your biology class. So the cell membranes are composed of this bilayer of lipid molecules, which have the hydrophilic part and the hydrophobic part. All right. And so the head points towards the aqueous solution, either inside the cell, the cytoplasm, or outside the cell, just whether it's blood or whether it's some sort of fluid. Okay, it's an aqueous solution. All right, so a cell membrane is another important application of this idea, how you have to take into account all of the intermolecular forces to really explain the behavior of the molecule in terms of solubility. Okay, so now let's talk about gas solubility in water in Henry's law. So this may not be intuitive to everybody. It is true that gases dissolve in water, okay? So how do you know that? Well, here's one way that you know that. We know that oxygen must dissolve in water at least a little bit because there are living things in the water, and those living things just need oxygen just like land-based life forms do. So that aquatic life has to get its oxygen from its environment, and so it gets it from the oxygen that's dissolved in the water. So aquatic life gets the oxygen needed for survival from those gases that are dissolved in the water. Huh? And so you might ask the question, well, wait a minute, if oxygen is a non-polar molecule, then how does this non-polar molecule get dissolved in a polar solvent like water? We just finished saying like dissolves like. So how is it that a nonpolar solute like oxygen can become dissolved in a polar solvent like water? Well, we've already learned this actually. It's through an induced dipole. Remember this? So here comes our nonpolar oxygen molecule, but then a water molecule comes along, which is polar, and induces in a temporary way a dipole in the oxygen. So the water molecule comes along and induces a dipole, and that's what allows the oxygen to become slightly soluble in water. It's that induced dipole intermolecular force at work. And so that's one reason for I guess I could say the primary reason for these non-polar gases like oxygen and nitrogen and carbon dioxide getting dissolved in water. Okay, so since gases dissolve in water, we want to talk about the factors that will affect how much they are dissolved in water. Okay. There's two. Temperature affects solubility, and the pressure of the gas affects solubility. So we'll go through how each one affects solubility. So first of all, temperature. So with temperature, it's all about kinetic energy. So when you're at low temperature, so if you have a low temperature, that's what this down arrow T is supposed to represent. That means that the gases that are dissolved in the water have less kinetic energy. So those intermolecular forces that exist between the gas and the water, that induced dipole we just talked about, are able to keep more of the gas dissolved. All right, because the gas molecules don't have enough kinetic energy to overcome those intermolecular forces that are holding the gas in the solution. All right, and it's just the opposite if you increase the temperature or if you're at a high temperature. In that case, the gases have more kinetic energy, and that kinetic energy is big enough to where it overcomes that solute-solvent interaction, and therefore you end up with reduced solubility. Okay, so at a high temperature, gases have more kinetic energy, which overcomes solute-solvent interactions and reduces the solubility. So the overall effect is this. When you're at a low temperature, it's like your gas molecules stay in solution because they're just kind of moving around with low kinetic energy. And so those intermolecular forces represent an energy that's greater than the kinetic energy of those gas molecules. Okay. So that's if you're at a low temperature. Well, what if you're at a high temperature? So if you're at a high temperature, those gas molecules have enough kinetic energy to overcome the intermolecular forces. So the kinetic energy is greater than the intermolecular forces. And so they will not stay in solution. And so that's why in this graph, you see as the temperature goes down, the solubility goes up. So gases are more soluble in water at low temperatures. And that's pretty counterintuitive because most people think that things become more soluble if you heat up the water. For example, that if you have iced tea and you put a tablespoon of sugar in it, that sugar just goes to the bottom, sinks to the bottom, does not dissolve in the iced tea. But if you have hot tea and you put the tablespoon of sugar in it and stir it up a little bit, it will dissolve in it. Well, that's the way it works with solids. But with gases, it's just the opposite. So as you decrease the temperature, you increase the solubility. Okay, so that's the impact of temperature. Now let's talk about the impact of pressure. Pressure, so in that case, what you need collisions. You need the gas molecules to collide with the surface of the water. And we know that pressure is related to the number of collisions. That's essentially one way to think about pressure. So the solubility of a gas in water depends on the partial pressure of the gas in the air above the surface of the liquid or the water, right? So it's proportional to the number of collisions. So the amount of gas that dissolves depends on the number of collisions that the gas molecules have with the surface. And it's proportional. So that if we increase the pressure of that gas hovering over the surface of the water, that's going to increase the number of collisions that occur between the gas and the surface of the water. And so that means that we're going to have increased amount of dissolved gas, or the solubility of the gas goes up. So as the pressure of the gas goes up, the solubility of the gas goes up. That's the bottom line of it. And here's just a picture of that. So again, if I have a piston in place here, and right now this could be a low pressure type situation, so there's no gas dissolved in the water because there's relatively small amount of collisions occurring. But if I push that piston down, then there's going to be more collisions occurring because it's a smaller volume, so the higher pressure, so more collisions occur. between the gas molecules and the surface of the water. And so that's going to lead to some of those gas molecules getting dissolved in the water. Okay. So that's the relationship there. So it's different based on the parameter. With temperature, the lower the temperature, the higher the solubility. With pressure, it's the higher the pressure, the higher the solubility. Okay? And so that's what's actually represented in Henry's law. Henry's law doesn't have to say much about temperature, except for the fact that the constant that's associated with Henry's law is temperature dependent. You'd have to have a table with Henry's law constant for each temperature. Now, I don't want you to memorize this equation. You don't even really have to know how to do calculations with this equation. It just, I want you to know that Henry's law is is sort of summarized by this equation and know the terms and what they represent. Okay, so there's actually some pretty cool applications of Henry's law that you deal with on a day-to-day basis. So first of all, well, not necessarily on a day-to-day basis, but this is just very interesting. So we said that gases are more soluble at cold temperatures and high pressures. And so if you go to like the depths of the Arctic Ocean, that's like a perfect scenario for that, because the water is very cold, and as you go down, the pressure gets higher, right? The water, the pressure that you experience as you go deeper and deeper and deeper is higher and higher. So that water in the Arctic Ocean down at the near the bottom is a situation where you can have a relatively large amount of oxygen dissolved in the water. And so because of that, there are some species of aquatic life that have adapted to that in interesting ways. So this fish, for example, as you can see, is very pale, and that's in large part because its blood is transparent. It's not red like other living organisms, right? And that's because it does not have hemoglobin. Remember, hemoglobin is the molecule that transports oxygen to the tissues everywhere in your body. But this fish does not need hemoglobin. So its blood is not red because it has no hemoglobin, right? And it doesn't need the hemoglobin because there's so much oxygen dissolved in the water down here, because it's so cold and because of the depth, that oxygen just, is in high enough concentration that it just kind of naturally diffuses into the tissues where it needs to be. And so there's this, this fish does not need hemoglobin, and so it's adapted in such a way that it doesn't have it. And so its blood is transparent. Okay, here's another one. If you enjoy scuba diving, this is something that you have to take into account. So when you go down below sea level, or into the water there, because the pressure is increasing. Remember, the deeper you go, the higher the pressure. And now we know that the solubility of a gas is dependent on the pressure. The higher the pressure, the more soluble the gas is. So as you go down into the water, the deeper you go, the more gas that gets dissolved into your blood. That's what this is representing. More gases are getting dissolved in your blood. Okay, so then if you decide to ascend back to the surface, you have to do that slowly, because if you don't, then what's going to happen is two things. First of all, as you ascend, the solubility of gases decreases because the pressure is decreasing. And so that means those gases are going to leave your blood. They're going to come out of your blood because they're not soluble in your blood anymore as much. Well, the other thing is, Boyle's law. There's a relationship between pressure and volume. So as you ascend, the pressure is going down, so the volume of those gas bubbles are going to increase. Okay, so the combination of the lesser and lesser solubility and Boyle's law, how the volume of the gas bubble is expanding, that can burst tiny little blood vessels, which is going to cause the damage to your tissues, but also the pain that's going to cause, because you'll have these gas bubbles expanding in your body. And so that's what you've heard of. If you ever heard of that condition called the bends, or technically it's called decompression sickness. Okay, that is a consequence of Henry's law. And so that's why you can't ascend. If you've been diving, you can't ascend too quickly. And that's why the treatment for it would be like a hyperbaric chamber. They put you in a chamber that has high pressures of oxygen, right? And so that's one way to treat it. Okay, so scuba diving is another application of Henry's law. And then finally, another one that you're certainly familiar with. Something happens like this. Have you ever opened a bottle of soda, and then as soon as you twist the cap, it just starts to come out everywhere? That also is an application of Henry's law, because when they bottled that soda, effectively there is 4 atmospheres of pressure of carbon dioxide in that bottle. Well, as soon as you twist that cap, it's experiencing the same atmosphere that you're breathing, which is less than 1%, so less than 0.01 atmospheres of carbon dioxide. So it goes from an environment of 4 atmospheres of carbon dioxide to an environment of less than 0.01 atmospheres of carbon dioxide. And so due to that difference in pressure of carbon dioxide, the solubility goes way down. And so that's why those gases are escaping and creating that stream of fizz, right?